Okay, in this video, I'm going to be talking about Taylor series and Maclaurin series, and how to, well, what they're for, I guess, but also and how to create them. So, Taylor series is a power series. It's a type of power series, but it's used to approximate other functions. So, and this is so basically, kind of like a power series, that when you write out the terms of it, it's just a really long polynomial. And the basic idea is that polynomials are the kind of most nicely functioning functions in the function world, because they're easy to take the derivative of, they're easy to integrate. The graphs are pretty straightforward. We know that the number of turning points is related to the degree of the polynomial. On and on and on. There's just so many different things about them that are very nice and easy to work with. So what the idea of a Taylor series is that you could take pretty much any function and you could turn it into a polynomial function. And this is the formula for doing it. Now this is on your help sheet, so you'll have that at any time on a test or quiz to use. But and then Maclaurin series is a type of Taylor series, a special type of Taylor series that's centered at 0. So Maclaurin series is just a Taylor series that's centered at 0. What's a Taylor series? A Taylor series is an infinite power series that is used to model some other function. Okay, so remember, you guys have been learning about power series. So power series, the difference is you have n's that are responding to the sigma notation, but then you have this extra variable under this that's an x. So that means that we can when we do a power series, we're representing a whole family of series, because if you put in a different number of x, you get out a different result. So all of the Taylor series will follow this form, which means all the Maclaurin series would follow a similar form, just that would look like this: n0, infinity. So that would be the Maclaurin series, because you just put in 0 for C. Whereas Taylor series, the generic, you could put whatever number you want in for C to figure out what the Taylor series is. So now there's one piece of notation here you may have not seen before. This terminology is just a way to write a bunch of higher order derivatives. So you know that when we write f prime of C, that would mean the derivative of the f function evaluated at C. Or if we write f double prime of C, that would equal this is derivative evaluated at C. This is the second derivative evaluated at C. So then it gets confusing if I have to write too many tick marks in there, because you can't tell what they are. So what we do, as we get to the higher order derivatives, we replace the tick marks with just a little number in parentheses. So this would be a third derivative evaluated at C. And this would be a fourth derivative evaluated at C. So that's just the notation that you need to understand. Of course, you should understand the power series or the sigma notation stuff. So we know that n goes up starts at 0. This says it starts at 0 and goes up 1 each time. So it would be n equals 0, n equals 1, 2, 3, 4, all the way up, right? So so that's what a Taylor series is. Now, this is important to understand, because the idea is that if you take for example, sine of pi over 4. Here's a good example. You can do that in your head, right? We all know that that's 1 over rad 2. But you also can do it in your calculator. And remember when in trigonometry, when we did sine of pi over 4, sometimes they would say, your teacher would say they want the exact answer, or you could do, other times they might be okay with the approximated version. And the only way you can get the exact answer is right here. So the way you get the approximated version is either you go to a table, which you guys don't use those anymore, or you use your calculator. Now here's the interesting thing that you may not know. When you type in sine of pi over 4 into your calculator, let's do that real quick. Sine of pi divided by 4, you get 0.01. Whoops, no you don't. I'm in degree mode. I think that looked right. Let's try that again. Sine of pi divided by 4. There we go. You get 0.707106 7812. Now you've probably always understood that that is the approximation, because there's more decimals off screen. That if you could just get to all those decimals, then you would have the exact value. Well, the truth of the matter is that that's not even the case, because when you type in sine of pi over 4 into calculator, the calculator is not going and looking on some chart or something and finding the exact value of sine of pi over 4. It's actually approximating pi over 4 itself by using a Taylor series, actually a partial sum of a Taylor series. So it's evaluating this by plugging pi over 4 into some multi-termed polynomial that's an approximation of sine of pi over 4. So that's the idea of what we're talking about here. So we can use Taylor series because it's pretty hard to tell a calculator to figure out the ratio of this opposite side over the hypotenuse side. So we have to just give it something to calculate. And so the easy thing for a calculator to calculate is just a really long polynomial. And it doesn't matter how long it is. It could have 100 terms, and the calculator will do that no problem. It doesn't, or the other thing a calculator cannot do is it cannot calculate a infinite polynomial. And that's why this is approximation. So, because it's gonna do the Taylor series, but it's only gonna do a certain part of it, which we call a partial sum. And that partial sum, actually, another name for it is a Taylor polynomial, because if we have a polynomial that comes from a Taylor series, if it's just a part of a Taylor series, then we call it a Taylor polynomial. Okay, so that's the idea. So what I want to show you in this video is how to generate a Taylor series from a given function. So for example, we'll start with a really easy one. F of x equals e to the x. That is a function that actually behaves pretty well on its own, but it's also really easy to calculate the Taylor series for it, so I thought we'd start with an easy one. Okay, so remember the formula for calculating the Taylor series. We're actually going to do Maclaurin series because we're going to center it at 0. So this would be from 0 to infinity, and it's going to have an n factorial on the bottom, and you're going to evaluate a bunch of derivatives, evaluate it at 0, and this is going to just be x to the n. Okay? So what we don't, the first part is easy. This is clearly x to the n and n factorial. We don't have to worry about that. That's part of the formula. The thing we don't know right at the hand is this. That's the thing that's unique from function to function. The n factorial and the x to the n is the same for every Taylor series. What's unique is this little function part. So what I need to do is evaluate different orders of the derivative of the f function. So for example, f of x equals e to the x. That would be f. That would be a 0 order derivative, right? And we want to evaluate that at c, which we said this is a Maclaurin series, so it should be 0. So that would be e to the 0, which of course would just be 1. So then if we take the first derivative, the derivative of e to the x, of course, is just e to the x. And that means that the first order derivative evaluated at 0 would still be e to the 0, which is just 1. And we don't have to go very far in this to see that that is just going to keep producing 1, because the derivative of e to the x is just e to the x. So the second order derivative evaluated at 0 would be e to the 0, which is still just 1. So what we discover is that this piece right here, the yellow piece, seems to be 1 no matter what derivative we're looking at. So then we can write the Maclaurin series for e to the x is just going to be x to the n over n factorial. And if you look at your help sheet I have right here, notice that's exactly what it is. You can see that right there. Okay? So now let's do one slightly more difficult. Let's say we're interested in finding the Taylor series for e to the 2x. So again, this won't be that much harder, but it'll illustrate how this works. Okay, so once again, we're doing the Maclaurin series, so we're evaluating at 0. That means we're going to start out with n running from 0 to infinity of f to the nth order, evaluated at 0, all over n factorial, and x minus 0, which should be x to the n. Okay, so I need to figure out the yellow part again. I need to figure out that part. That's the part I don't know. Okay, so I go over here and begin taking derivatives. So f of x, which is the 0 order derivative, so that would give me f, the 0 order derivative evaluated at 0. That would be e to the 0, because 2 times 0 is 0, which would just be 1. Okay, now f prime of x would be 2 times e to the 2x. So then my first order derivative evaluated at 0 would be 2 times e to the 0, which would be 2 times 1, which would just be 2. F double prime of x is 4, because the chain rule kicks out of 2 again, e to the 2x. So that would be the second order derivative, and that would end up being 4 times e to the 0, which would just be 4. And again, we don't have to go very far in this, that we see the pattern. We see that each new order of the derivative just gets another power of 2. And just to make that even clearer, notice here, this is n equals 0, n equals 1, n equals 2, right? So that means that this seems to be 2 to the 0, 2 to the first, 2 to the second. We see the pattern that the power of 2 is the same as the n. So then we can rewrite this as my Maclaurin series for e to the 2x is going to be 2 to the n times x to the n all over n factorial. So this would be a Taylor series, a Maclaurin series, which is a Taylor series centered at 0, that you could use to evaluate e to the 2x. Okay, let's do one more example. Let's do f of x equals 1 over x squared. And we'll evaluate that centered at 1. So the center is 1. So then that means we need this. N runs from 0 to infinity of the nth order, evaluated at 1, all over n factorial times x minus 1 to the n. So again, the n factorial and the x minus 1 to the n is always there. That's a part of every Taylor series. And this is the part that we don't know. So we need to figure that out. Okay, so here we go. This is us figuring it out. So f of 1 would be equal to 1 over 1, which is just 1. F prime of 1, that's the first derivative. So remember the first derivative. So that would be, maybe we'll do this so you can see what's going on. We'll start off with an x. So that would be what? Negative x. Nope. negative 2 times x to the negative 3 is what it would be, right? And that means that f prime evaluated at 1 would just be negative 2. Okay? Now, let's go for the second order derivative. That's going to be 6x to the negative 4. So that means f second order derivative evaluated at 1 would just be 6. Because 1 over 1 to the 4th is 1. So then we do f third order derivative would be negative 24x to the negative 4. That means the third order derivative evaluated at 1 would be negative 24. And it looks like, hopefully at this point you see a pattern. You see, like, it seems like we're multiplying by an increasing number. And then again, it's helpful to go back and say, okay, this is n equals 0, this is n equals 1, n equals 2, n equals 3, okay? So, and this is 1, negative 2, 6, negative 24. So if we look at the 0, 1, 2, 3, that's, it might be helpful to write this the way it was produced. This is 3 times 2. This is 4 times 3 times 2. And when you write it like that, you can see that it looks like there's a factorial going on here, doesn't it? But there's also an alternating thing going on. So could we write this as, so let's do 3 to the n. No, sorry, 3 to the n. Let's do f of the nth order. That seems like it might be, evaluated 1. It seems like it must be some factorial. Let's compare. This is n equals 3, and that's 4 factorial. N equals 2, 3 factorial. N equals 1, 2 factorial. N equals 0, 1 factorial. So it seems like the factorial is always 1 above the n. So could this be n plus 1 factorial? N plus 1 factorial. And I think that would take care of the 4, 3, 2, 3, 2, 2, 1. But also there's a negative alternating there. So could we do a negative 1 to the n? And let's just check to make sure that works. If we have negative this, because this would be, that means this would be negative 1 to the 0 power. And this would have a negative 1 to the first power. This would have a negative 1 to the second power. And it looks like it's matching up because I'm getting positive negative when I want. So that means, so then this is my expression. So let's go back up here and put it in. So now we have n running from 0 to infinity of n plus 1 factorial times, times negative 1 to the n times x minus 1 to the n all over n factorial. Now we know how to handle factorials pretty good because we've been doing it with the power series stuff, right? Or the ratio test. So notice that when n factorial is divided by n, we're left with just n plus 1. We'll put the negative 1. I should have made more room for that. I always like to put the negative 1 out front. I don't know why, actually. It looks better. And then times n plus 1 times x minus 1 to the n. Because the n factorial is not there anymore because it canceled with that, leaving just n plus 1. So this would be a Taylor series for 1 over x squared centered at 1. All right.